Assalamualaikum and hi, my name is Siti Namadia binti Muhammad Syam. My metric number is CF230072 and I'll present the introductions. This slide introduces shear force and bending moment in beam. Shear force is an internal force that is parallel to the cross sections and usually higher near the support, where failure may occur if resistance is insufficient. Bending moment cause the beam to bend under applied load and is calculated as the sum of moment at a point along the beam. Both are important for ensuring structure safety and proper design.
Next, for the background, analyze a real reinforced concrete frame building system to understand how its various structural elements. The project includes selecting real structure component from actual building, which is a beam at a bangunan F-cup, and calculating their internal reaction, shear force, bending moment, stresses, and the deflection.
So I am Azka Saleh. I am presenting about the problem statement. So for the problem statement, it is in real world application. Structural elements such as beams and frames are constantly subjected to various types of loads, including dead loads from the structure of point weight, live loads, and from occupants of usage, and sometimes environmental loads. These loads act simultaneously and influence how the structure behaves under service condition. Without proper structural analysis, the structure may experience excessive deflection, such as cracking or even failure, which can compromise safety and functionality. Therefore, understanding how loads are transferred through structural members and support is critical to ensuring that the structure performs as intended. This project focuses on analyzing the behavior of a frame structure under assumed loading condition and specific support types. By evaluate internal forces, reaction, and bending moments. By evaluate internal forces, reaction, bending moments, shear force, and deflection, the structural adequacy can be assessed. The results allows us to verify whether the structure satisfies both strength and service stability requirements, ensuring it is safe, stable, and suitable for practical use.
Okey, Assalamualaikum dan selamat sejahtera. Saya Nur Anis Husna binti Muhammad Daud. Nombor metrik saya CF240046. Jadi, saya akan menerangkan berkenaan objektif bagi kajian kes dari kumpulan kami. Untuk objektif yang pertama, kita mengira semua beban yang bertindak ke atas struktur seperti beban mati, beban hidup dan beban persekitaran berdasarkan prinsip daripada kejuruteraan dan piawaian yang berkaitan. Objektif yang kedua adalah kita menganalisis struktur rangka sebenar dengan mengenal pasti bentuk, jenis sokongan dan komponen struktur melalui lukisan skematik yang jelas. Objektif yang seterusnya adalah menentukan daya dalaman seperti daya Ricci, momen lentur dan tindak balas sokongan menggunakan kaedah analisis. Objektif yang keempat adalah mengira tegasan serta menunjukkan pengagihannya menggunakan rajah tegasan. Yang terakhir adalah menilai pesongan struktur dan membentangkan semula hasil analisis menggunakan rajah seperti SFT, BMD dan rajah pengagihan tegasan. Okey, bagi location yang saya pilih adalah di Wisma Inn. Gambar rajah boleh dilihat dalam slide. Jadinya saya akan kira, yang pertama sekali saya akan kira untuk depth load. Okey, untuk depth load, pertama sekali kita akan mengenal pasti specific weight untuk konkrit. Spesifik untuk konkrit ini adalah untuk standard konkrit adalah 25 kN per meter square. Okey, untuk menilai volume untuk beam ni kita akan darabkan dengan panjang, darat lebar, darat tinggi. Jadi panjang di sini adalah 150 mm, panjang dia adalah 600 mm dan lebar dia adalah 305 meter. Jadi, saya akan convertkan nilai milimeter ni kepada meter. Jadi, senang untuk kita kira lah, untuk kita tetapkan unit dia dalam kilonewton per meter. Okey, untuk volume beam, saya akan darabkan 0.6 darabkan dengan 0.15 darabkan dengan 3.05. Jadi, nilai volumenya adalah 2.75 mm square. Okey, untuk weight of concrete, kita akan darabkan dengan weight konkrit iaitu 25 timeskan dengan 10 kuasa 3 darabkan dengan volume beam iaitu 2.75. So untuk weight of concrete kita akan dapat hasil 68.75 kilonewton. Untuk uniform distribution load untuk safe weight beam, kita akan bahagikan nilai weight konkrit dengan volume beam iaitu 68.75 kilonewton kita bahagikan dengan 68.75 bahagikan dengan 3.05 iaitu lebar daripada beam tersebut. So dia akan mendapat 22.54 kilonewton per meter. Untuk live load, kita akan ambil nilai lebar saya darabkan dengan nilai live load. Jadi nilai live load kita adalah 2.0 kilonewton per meter kuasa 2. Jadinya 3.05 darabkan dengan 2.0 saya akan sama dengan 6.1 kilonewton per meter. Okey, untuk environmental loads kita akan kira untuk angin dan air. Jadinya di sini pertama sekali saya akan kira untuk nilai GK dan QK. Jadi untuk angin saya akan ambil nilai weight untuk angin adalah 0.8. Saya darabkan dengan lebar daripada beam tersebut adalah 3.05 meter. Jadi dia akan dapat 2.44 kilonewton per meter. Untuk hujan pula 0.3 adalah nilai untuk hujan iaitu saya darabkan dengan 3.05 meter. Kita akan menjadi 0.92 kilonewton per meter. Alright. Untuk GK dan QK, saya ambil 1.5 GK, saya darabkan dengan 2.44 dan saya tambahkan dengan 1.5 QK. Nilai QK saya adalah 0.92. Saya mendapat 4.75. Okey, bagi step seterusnya adalah saya melukis free body diagram iaitu seperti yang dalam slide tu. Jadinya saya punya UDL adalah 4.75. Nilai itu saya dapat daripada hasil tambah GK dan QK daripada angin dan hujan. Alright. Untuk calculation untuk SFD dan BMD saya akan kira untuk moment terlebih dahulu. Okey, nilai moment total moment A sama dengan kosong. Okey, jadinya 4.75 saya darabkan dengan 3.05 iaitu panjang dia. Disebabkan UDL saya bahagikan dia dengan 2 lagi. So tolakkan dengan BY, jarak dia adalah 3.05 sama dengan kosong. Jadinya hasil daripada tu saya dapat 22.0934 sama dengan saya pindahkan 3.05 BY ke sebelah sana. Jadinya dia akan menjadi BY sama dengan 7.24 kilonewton. Okey, untuk nilai FY pula, saya membuat hasil tambah AY tambah dengan BY, saya tolakkan dengan 4.75 darabkan dengan 3.05 sama dengan kosong. Jadinya hasil yang dapat adalah AY sama dengan 7.24 kilonewton. Okey, total Fx adalah sama dengan kosong. Okey, selepas daripada itu saya akan terus mengira, saya akan lukis free body diagram dan mengikuti dengan shear force diagram dengan bending moment diagram. Berikut adalah shear force diagram dan bending moment diagram yang saya dapat. Hasil kedua SFD dan BMD saya dapat kosong. Okey, selepas daripada hasilan daripada SFD dan BMD, saya terus mengira maximum shear force. Okey, untuk maximum shear force saya akan dapat daripada nilai SFD iaitu 7.24 dan maximum bending moment dapat daripada bending moment diagram. So iaitu 7.24. Okey. Untuk Total moment sama dengan untuk moment max sama dengan 7.24 saya darabkan dengan 1.525 saya darabkan dengan 1.2 sama dengan 5.5. Okey, step seterusnya adalah mengira maximum shear stress. Untuk maximum shear stress, saya akan menggunakan ISX iaitu 2.7 darabkan dengan 10 kuasa negatif 3 meter kuasa 4. Dan Y bar saya sama dengan 0.3 meter. Jadinya A saya akan darabkan dengan Y iaitu 0.15 saya darabkan dengan 0.6 saya darabkan dengan 0.3 menjadi 0.027 meter kuasa 3. Untuk T max saya menggunakan formula VA Y bar bahagikan dengan IT. Jadi 7.24 saya darabkan dengan 10 kuasa 3 saya darabkan dengan 0.027 bahagikan dengan 2.7 darab 10 kuasa negatif 3 darabkan dengan 0.13 menjadi 482.67 darab 10 kuasa 3 Newton meter. Berikut adalah gambar untuk maximum shear stress. Bagi deflection pula, itu adalah gambar rajah untuk deflection. Saya masukkan balik nilai AY, BY. Saya mengira E sama dengan 25 darabkan dengan 10 kuasa 9 Pascal. So I saya adalah 2.7 darab dengan 10 kuasa 3 Newton per meter square. Okey, jadinya untuk calculation untuk EI adalah 25 darabkan dengan 10 kuasa 9 darabkan dengan 2.7 darab 10 kuasa negatif 3. Hasil telan dia adalah 67.5 darab 10 kuasa 6 Newton per meter kuasa 2. Alright, untuk maksimum untuk MX, untuk mengira MX adalah sama dengan negatif MA saya tolakkan dengan V maksimum saya tambah dengan W X kuasa 2 bahagi dengan 2. Jadi MX sama dengan negatif saya letakkan dalam kurungan sama dengan negatif 3680 saya tolakkan dengan 4750 X saya tambahkan dengan 4750 X kuasa 2 bahagikan dengan 2. Hasilan dapatan dia adalah 3680 saya tolak dengan 4750 X saya tambahkan dengan 2285 X kuasa 2. MA dengan VMA tu saya dapat daripada bending moment dengan shear force diagram. Okey, untuk step seterusnya adalah Maclaurin method. So untuk Maclaurin method saya menggunakan formula yang dipaparkan iaitu EI D kuasa 2Y per dengan DX kuasa 2. Okey, formula yang kedua jadinya untuk formula ini saya akan menggunakan nilai 3680 saya tolakkan dengan 4750X saya tambahkan dengan 2285X kuasa 2. Nilai MX yang saya dapat tadi bila saya dah kira di atas tadi. Jadi seterusnya saya mencari nilai C1. Jadinya untuk EI dy per dx sama dengan 3680x tolakkan dengan 4750x kuasa 2 bahagikan dengan 2 saya tambahkan dengan 2285x kuasa 3 bahagikan dengan 3 tambah dengan C1. Okey, jadi saya dapat satu equation iaitu 3680x saya tolakkan dengan 2375x kuasa 2 tambahkan dengan 761.67x kuasa 3 tambahkan dengan C1. Alright, untuk EIY untuk equationnya adalah 3680x kuasa 2 bahagikan dengan 2 tolakkan dengan 2375x kuasa 3 bahagi dengan 3 tambahkan dengan 761.67x kuasa 4 bahagi dengan 4 saya tambahkan dengan C1x tambah dengan C2. Jadi equation itu mendapat 1840x kuasa 2 tolak dengan 7691.67x kuasa 3 tambahkan dengan 190.67 42X kuasa 4 tambah dengan C1X tambah dengan C2. Alright, untuk seterusnya, saya masukkan nilai X sama dengan kosong, Y sama dengan kosong dalam equation EI dalam bracket Y. So, saya mendapat C2 sama dengan kosong. Okey, untuk seterusnya, saya menukarkan nombor X sama dengan 3.05 dan Y sama dengan kosong. So, hasil dapatan dia adalah C1 sama dengan negatif 3650.21. Okey, untuk equation EI dy per dx, hasil equationnya adalah 3680x tolak dengan 2375x kuasa 2 tambah dengan 761.67x kuasa 3 tolakkan dengan 3650.21. Untuk EIY, hasil dapatannya adalah 18400x kuasa 2 tolak dengan 791.67x kuasa 3 tambahkan dengan 190.42x kuasa 4 tolak dengan 3650.21x. Jadi, untuk deflection adalah X sama dengan 1. Jadinya Y sama dengan nilai Y kita adalah 67.5 darab dengan 10 kuasa 6Y sama dengan negatif 241.46. Jadi Y sama dengan negatif 241.46 bahagikan dengan 67.5 darab 10 kuasa 6. So Y kita adalah negatif 3.575 darab dengan 10 kuasa negatif 5 meter dan Y sama dengan negatif 0.00036 mm. Sekian, itu sahaja daripada saya. Terima kasih.
Assalamualaikum. So today I will be presenting about the structural beam analysis to carry out for this project, which is the beam that I circled in the picture. Today, the objective of the analysis is to determine the support reaction, internal forces, and structural behavior of the beam under applied loading, and to ensure that the beam is structurally safe and performs within acceptable limits. As for the structure I choose is a bus station at UTHM near ATM. As for the beam, I consider in the analysis is modeled as a simply supported beam with a span length of 3 meters. The beam is subjected to a UDL or uniformly distributed load that represent the design loading condition. For simplification and consistency with theory, deflection are assumed to be small, loads are applied statically, self-weight and imposed loads are included in the total design load. And as for the structural calculation, I put in the slide as shown below, as shown in the slide. As for the width, I choose the B is 0.3 meter and the height is 0.5 meter. From the identification of the roof sheet type, from the photo is shown about the metal roof sheeting that is use a metal deck that commonly used for a bus stops or shelters. It is a typical materials use a zinc or aluminium or metal deck sheet with a thickness of 0.4 to 0.6 mm. As for the self-weight of the beam, for the analysis, I choose which is the self-weight of the beam, which is P times H times L. I got it as 0.45 meter cube, and as for the width of the beam, 0.5 meter times width 24 kilonewton per meter cube, which is the density of RC that I refer from Google, that usually approximately from 24 to 25 kilonewton per meter cube. So I convert it to UDL, which is dead load, from which is 11.25 kilonewton divided with the length of the beam, which is 3 meter. I got it as 3.75 kilonewton per meter. For the roof type, it is a metal deck, which is with a unit weight of in range of 0.10 to 0.15, and as for the including purlins and finishing, it is from 0.20 to 0.30. So I choose the total weight for roof type for the roof is 0.25 kilonewton per meter cube. And as for the roof sheeting and secondary members, but there's no purlins including in my calculation. So for the density of the steel, I got it as 78.5 kilonewton per meter cube. I got it from Google, which is the assumption and the normal density of the steel, and I assume for the thickness as 0.005 meter. As for the total weight, the density times P times gravity, which is I got it is 0.04 kilonewton per meter. To obtain unit weight of roof sheeting, I use standard engineering values, which is typical weight of metal roof sheeting that I shown in the slide. As for the spacing between the beam, which is the tributary width, I make an assumption it is which is I got it as 3.0 meter, which is the weight of the roof equals to roof load times tributary width, which is I got is for roof load 0.25 times with the tributary width 3.0, which is I got as 0.75 kilonewton per meter. Tributary width is the portion of a roof area which load is carried by a particular beam. For uniformly spaced beams, it is taken as a half the spacing to the adjacent beam and each side. As for environmental load, which is for the wind, rain or maintenance, I assume as 1.0 kilonewton per meter. So for the life load, for the environmental, the environmental load plus with the weight of the roof, which is 0.75. So the total of life load is 1.75 kilonewton per meter. So for the total design load, which is dead load plus life load, which is the equation is 1.35 GK plus 1.5 GK. So total out I got for the total design is 7.64 kilonewton per meter. As the applied loading on the beam consists of total design load of 7.64 kilonewton per meter, which is acting along the span. This load represents the combined effects of dead load and life load. The loading diagram was first drawn to clearly visualize how the load is distributed along the beam before proceed with calculation. The first step in the beam analysis is to determine the support reaction using the EOE, which is equation of equilibrium, to sum of the vertical and horizontal forces equals to 0, and as for the sum of moments equals to 0. By taking moments about one support and solve the equilibrium equation, the reaction force at the support will calculate. This reaction ensures that the beam remains in static equilibrium under the applied loading. Next, the SFT along the beam was determined. Start from the left support, shear force values were calculated at critical points such as at the support, at points and of load application, and at the mid-span where applicable. These values were then plot to the form of SFD. That helps me to identify the maximum shear force, regions of positive and negative shear, and the critical section that may govern shear design. And as for the SFPMD, I use the shear force results for the bending moment at key section along the beam was calculated. The bending moment diagram was then constructed, showing how bending varies along the span. The maximum bending moment, which usually occurs at mid-span or at the fixed end, is a critical value because it governs at the bending stress and beam design. The maximum bending moment obtained. The bending stress in the beam was calculated using the bending stress equation, where it is sigma equals to my over I. From the equation, sigma equals to my over I, which is m is the bending moment, y is the distance from the natural axis, and I is the second moment of area. The calculated bending stress was then compared with the allowable stress of the material to verify that the beam is safe under bending. And as for the deflection analysis, it is to strengthen the service stability was checked by calculating the beam deflection. Using the standard beam deflection equation for the given loading and support condition, the maximum deflection was determined. The calculated deflection was found to be within the allowable width limit, ensuring that the beam will not experience excessive sagging or discomfort during service. As from the analysis, support reaction satisfy equilibrium, maximum shear force and bending moment are within acceptable limits, bending stress does not exceed the material's allowable stress, and the deflection complies with service stability requirements. This indicates that the beam performs safely and efficiently under the applied loading. In conclusion, the beam analysis has successfully demonstrated that the beam is structurally determined under the given loading conditions. The calculation of support reaction, shear force, bending moment, stress and deflection confirm that both strength and surface stability criteria are satisfied. This analysis provides the confidence that the beam design is safe and suitable for practical application. That's all from me. Thank you and have a nice day. As for the load distribution, the applied load on the beam originates from the support structural elements above, such as the finished imposed load, which is dead load. These loads are first transferred to the beam through a tributary weight, which represents the portion of the area contributing load to the beam. As for tributary area concept, the tributary is defined as the area of the slab as the area that is supported by the beam. Half the distance to the adjacent beam on either side is taken as the effective weight contributing load, which is the metal deck didn't directly transfer the load to the beam. It is transferred to the columns because there's some macam ada tiang dekat dekat tepi of the metal deck, so that's why it is not transfer directly to the beam.
So this is my chosen locations, which is Gazebo PKU, just beside the PKU buildings. And I choose the beam that support the roof. Next is calculations. So this is my beam calculations. The load in are first identified and converted into a UDL. So the total UDL on the beam calculated as 4.4 kilonewton per meter, and consisting of dead load 0.95 kilonewton per meter, then live load 3.0 kilonewton per meter. Live load including the birds, the small animal and so on. And then environmental load 0.45 kilonewton per meter. Environmental load I calculate for rain and for wind. Then this resulted total UDL of 4.4 kilonewton. So producing equals support reaction of 0.0 kilonewton at both ends. Then the maximum bending moment occurred at midspan with a value of 4.95 kilonewton meter, while the maximum shear force at the support was 6.6 kilonewton, and then the corresponding maximum bending stress and shear stress were 26.4 megapascal and 1.32 megapascal respectively, and the maximum deflections was calculated as 3.29 meter occurring at midspan. So this indicating acceptable structure performance under the applied loads.
Assalamualaikum, my name is Adriana Azwani. I will continue my part. For this project, I select a corridor beam at level 8 at bangunan F-cup. The beam has a span of 4.0 meter and cross-section of 300 by 500 millimeter. It is a model as a simply supported beam. The beam carry two types of load, dead load and live load. The dead load include the beam self-weight, slab load and floor load, when the live load represent the corridor usage and maintenance. For this slide, I calculate the load acting on the beam. The total load is obtained by adding the beam self-weight, slab load and floor load, and is applied as a UDL, uniformly distributed load. The live load is taken as 2.0 kilonewton per square meter and convert into a line load using the tributary width. By combining the dead load and live load, the total uniformly distributed load on the beam is obtained. Next is structure analysis. The beam is subjected to UDL of 10.2 kilonewton per meter over a span of 4.0 meter. Since the beam is simply supported and the loading is symmetrical, the reaction at both support are equal with a 20.4 kilonewton at support A and support B. The shear force diagram shows the maximum shear force at a support and zero shear at a midspan. The bending moment diagram has a parabolic shape with the maximum bending moment occurred at the midspan. The shear force and bending moment come from the same loading. They represent the different quantity and have a different unit. Last slide is stress and deflection analysis. The maximum shear force is used to calculate the maximum shear stress which occur at the neutral axis. The calculated shear stress is within the allowable limit. The maximum deflection occurs at a midspan and is smaller than the allowable limit of L over 250. This diagram shows the load flow where slab and live load act on the beam, then transfer to support, column and foundation. In conclusion, the corridor beam is structurally safe and satisfies both strain and serviceability requirement. Thank you. Assalamualaikum, my name is Adelina Hazwani and I will continue my part. This structure is located at the front facade of Block G3 UTHM, which is an academic building mainly used for lecture hall and technique activities. As shown in the image, the selected beam is positioned at the main entrance and is idealized as a simply supported beam. The beam has a span of 50 meters with a width of 300 millimeters and a height of 500 millimeters as indicated in the diagram. The building is constructed using a reinforced concrete frame system consisting of beam, columns and slabs. Due to its clear visibility and accessibility, this beam is suitable for one-side observation, sketching and simplified structure analysis. First, I calculated the dead load on the beam. The concrete slab thickness is 150 mm, which is converted to 0.15 meter. Using a concrete density of 24 km per cube meter, the slab load is 3.6 km per square meter. After adding ceiling and the floor finishes, the total area load becomes 4.x kilonewtons per square meter. With a tributary width of 3 meters, the line load is 14.4 kilonewton per meter. Adding the beam slab width of 3.6 kilonewton per meter, the total dead load or UDL is 18.0 kilonewtons per meter. Life load and environmental load are neglected, so the total is 18.0 kilonewton per meter. This section continues with the structural response of the beam under the same UDL. From the equilibrium analysis, the reaction at both support are 135 kilonewton, which are then used to construct the shear force and bending moment diagrams. The maximum shear force occurred at the support with a value of 135 kilonewton, while the maximum bending moment of 506.25 kilonewton per meter occurs at the midspan. Based on the rectangular cross-section, the calculated maximum bending stress is about 40.5 megapascal and the maximum shear stress is approximately 1.35 megapascal, which represent the critical stress in the beam. Based on the calculation, this analysis determines the deflection of a simply supported beam subjected to a UDL. The material and section properties used are Young modulus of 25 times 10 to the power 9 pascals, a moment of inertia of 0.003125 meter to the power 4, and a span length of 50 meters. The UDL acting on the beam is 18 kilonewton per meter. Using the standard maximum deflection formula for a simply supported beam, the maximum deflection is calculated as approximately 0.152 meters or 152 millimeters. This maximum deflection occurs at midspan, while the deflection at both support is 0, confirming the expected behavior on the beam. In conclusion, this study evaluated the structure behavior of several beams from real-life structures, including Wisdom Inn, Block G3, the FCAP corridor, a gazebo near the Pusat Kesihatan University, and a bus station. Each beam was analysed using standard mechanics of materials principle to determine shear force, bending moment, stress, and deflection under applied loads. The results show that maximum shear force occurs near the support, while maximum bending moment occurs at the midspan, which agree with theoretical behavior. All calculated stress and deflection were within acceptable limits, indicating that the beams are structurally educated. Both timber and reinforced concrete beam were found to perform safely when properly designed. However, regular inspection and proper load control are important to prevent long-term damage. Overall, this project demonstrates the importance of accurate load estimation and structure analysis in safe beam design. That's all from our group. Thank you.